So my name is Cam. I graduated from Iowa State last year, and I moved on to become a faculty member in the University of Wyoming. So I've lived here about 5 years, and before that I was undergrad, and I have my master's back in the 90s, so from Iowa State too. So it's good to be back in Ames and Iowa. This presentation is pretty much about statistical analysis. For those who like statistics, it'll be a good one. I'll give you a review of some basic statistical theories behind the LRFD calibration process. So what we're going to learn from this presentation is LRFD calibration process, how we come up with those numbers, how we could integrate the power setup into the LRFD, construction control consideration, and recommended resistance factors that we develop and come up with for design as well as for construction. As we know, every time we estimate loads or resistance, it's not going to be a single number. It's going to be a variation of resistance, variations of load. Right? So we can characterize them or define them in a distribution. Look like this. So you have a distribution of load and as well as the distribution of resistance. Okay? And the two main parameters that describe the distribution, the mean and the standard deviation. Okay? So if the load is greater than the resistance, we will say that the system failed, which means that the foundation is insufficient to support the load. So in this region where it overlaps, the load could be higher than the resistance, as that defines the failure region. All right, consider a possible failure in the system. If we combine these two distribution into one, you see that on this graph that on the x-axis is the difference between resistance and the load. So R is resistance, Q is the load. If you have resistance smaller than load, then the difference should be a negative value that falls below 0. Right? And you have that distribution describe the difference between resistance and load. Okay, let's look at this region. This region is where the resistance is smaller than the load, and that region we define as failure region. Okay, and it is controlled by a distance from the mean of the distribution to this y-axis. What if I able to shift the distribution away from the y-axis? What do you see at this region? It's going to be a smaller region, right? So which means that your probability of failure, your chances of failure reduce. From a big region to a smaller region, if we could increase this distance from the y-axis to the mean of the distribution. All right? So that distance can be described by these two main parameters. One is the beta, that is defined as the reliability index. And the second parameter is the standard deviation of the distribution. All right? So if we can define this beta value, we could control the failure regions. We could define what will be our probability of failure of our design of our system. Right? That's the whole theory about the reliability theory, the whole principle behind the reliability theory, defined based on this beta value, based on the distribution of the resistance and the load. All right, and this is a very complex equation that developed, proposed by Barker in '91. And I do not expect you to use this equation in your foundation design. All right? Just to make sure that today, although it's Halloween, but it looks scary, but But I want to show you the background, how we come up with this number. Right? So all these parameters are recommended by AASHTO. We're adopting the AASHTO statistical parameters. For example, the load factors. For the dead load and the live load, the load bias basically is the mean of the dead load, mean of the live load, the coefficient of variations, the ratio of the dead load to the live load, as well as the beta value, the reliability index that control the probability of failure at the failure region. All right, we adopted the numbers proposed by AASHTO. But what are the difference between the AASHTO and the Iowa? Is these two parameters, the resistance bias and the coefficient of our resistance distribution. Right? These two values are based on the Iowa historical data. It's based on historical data and the 10 field tests that we performed a few years ago. That come up, these two numbers that reflect our local soil condition, that reflect our methodology of design foundation, that reflect our design as well as the construction practice in Iowa. That numbers reflect the local condition and input into this equation and come up with these resistance factors. Okay? And the new topic that introduced into this new LRFD design procedure is this important power setup, right? Because of the benefit of setup that we gain the capacity, we think that the benefit could eventually transfer into reducing the cost of our foundation. So, but is how we could integrate this power setup component into the LRFD limit state equation given by this. So this is the standard limit state equation. We have the factor load factor multiplied to the load, and we have this resistance multiplied to resistance factors multiplied to the resistance. But now you have two components of resistance, right? One is the resistance that you measured at the end of driving, and the second is the power setup resistance, the gain as a function of time. But how do we could able to put it into that form of equation? So we break it into two. So you have this resistance for end of driving multiplied to the resistance factors multiplied to the resistance that you measured at the end of driving, either by whip or by cab web, PDA, and plus the resistance factors for setup component multiplied to the setup in resistance, which is the net increase in the capacity. All right? Why there's two components here? Because this REOD is estimated using one method, whip or PDA cab web. Right? And this component is estimated by different approach, by this chart. Both are two different things. Both have their own uncertainties, right? The accuracy of estimating each of them are different. So for that reason, we come up with two components in this equation. And how you could quantify this R setup is we come up with this chart based on a tedious analysis that we perform over years and come up with this simple chart that allows you to use in design based on the weight average SPTN value. Okay? So, and further, and we want to know how we could estimate this guy here, the fee setup, right? And make the equation more complex now, right? And again, I do not expect you to use this equation, and able to develop a much complex equation, but eventually the goal is to quantify these numbers, right? Fee setup, and we will show you the numbers in the following slides. So the analysis was based on a database of 90 for static analysis method, and for construction control like WIP, it's based on 41 power load tests. distributed based on the soil types. Let's define this parameter, important parameter that control the probability or chances of failure. So the reliability index or the beta value is either 3.00 that is recommended by AASHTO or 2.33 also recommended by AASHTO, that based on whether the power group is redundant or non-redundant. Right? In Iowa, if it's an abutment, we define the power group as non-redundant if you have 3 or fewer pounds per power cap. All right? If it's other structures, we would say that we have 4 or fewer pounds per power cap, and in this category, we'll consider that as a non-redundant pulse. In opposite, we will use a beta value of 2.33 if it's redundant pulse, where in the abutment, you have 4 or more pounds per power group, or in other structures, you have 5 or more pounds per power cap. So the question is, you have a larger beta value, 3.00 than 2.33. Will this give you a smaller failure region or larger failure region? If you shifted the curve away from the y-axis because the beta is a larger number, so you will have larger or smaller? Smaller failure regions. Right? Why we want to have a smaller failure region in non-redundant power group? Because smaller the number of size of the power group is, each power contribute critically to the structures. Right? One fail will not able to distribute the load to other foundation or piles. For that reason, we want to increase the reliability of the structure and reduce the probability of failure. Right? We couldn't afford to have a higher probability of failure in non-redundant piles. Right? For that reason, that the higher number is chosen as opposed to this a smaller value for a non-redundant piles. This to show you a result of the resistance factors we calculate using that complex equation and compare with a range of reliability index. All right. So as you can see, as the reliability index increase, we want to have a smaller failure region or smaller chances of failure, that we got to have a smaller resistance factors. Right? So think about that. Higher factor of safety, right? Smaller chances of you're going to fail. Right? Same thing here. Reliability index increase, and you will end up with a smaller resistance factors. Right? And in each of the methods, we use Blue Book, we use other statistical methods, but we want to know which method gives you the best efficiency in terms of estimating the power capacity. So if you look at the solid line, the black solid line, that is based on the Iowa Blue Book. As compared with the others method, we found that the Blue Book, among the others, give you the best estimation of the power capacity. It's consistent as what we have used, and for that reason, we recommended the Blue Book as our design method as opposed to other various static methods. Right? So it's good news that we keep continuing using the Iowa Blue Book as it is the most efficient method in Iowa. So we recommended the design approach using Iowa Blue Book, right? And construction control can be using Iowa modified ENR formula, or WIP, or PDA CAPWEB, or static load test. All right? I think this is pretty much aligned with what your current practice is, because you're using Blue Book for design, and you use either WIP or ENR formula for construction control. And we're not changing that approach, but we're improving what you have right now. All right, and this is another set of analysis. Basically, is to minimize. We try to minimize the differences between the capacity we estimate using Blue Book and the capacity that you determine in the field using WIP or CAD web or ENR formulas, right? Because both capacities are estimated by different methods. So it bounds to have discrepancy in terms of matching the capacity. So what we try to do is we try to minimize that. It is again, I'm not going to go through that analysis process. It's described in your volume 3 if you're interested to know how it could, was performed to come up with all this number. We found that this is the originally determined resistance factors for I/O blue book. After considering the construction control analysis, we able to increase some of the resistance factors further. Right? For example, if it's a mixed site, if we use WIP as a construction control, we could increase from 0.6 to 0.64 after considering the construction control using WIP. So that has been included in the recommended resistance factors for design using Blue Book. Right? This is to show you the distribution before and after considering the construction control. The main point here is that you look at the mean of the distribution before considering the construction control, and it shifted to ratio 1, which means that the capacity estimated by WIP is matching with the capacity estimated by Blue Book in average. All right? So we're able to match that, the average value, to 1. And this is the first time maybe you see the recommended resistance factors. Don't be scared by all the series of numbers. Right now you're using one single number, but this is the table that summarizes the resistance factors that for design of PAL using Iowa Blue Book. Okay? But it changes with the type of construction control method that you specified during the design stage, that this method is the method I select for construction control in the future during construction. So with that, you have a series of different resistance factors based on the different construction control method, and plus it is also depending on the type of soil profile you have along the pile length. All right? For example, if you use the Iowa DOT ENR formula as your construction control, and it is in the clay soil profile or cohesive materials, then the resistance factors is 0.6. All right? If you use WIP as your construction control, under the cohesive materials, your resistance factors will be 0.65. But again, we were repeating throughout this today and show you the how you could choose the right numbers from this table. Right? This is to give you an idea what you're going to see in the rest of the following presentations. So this is a design, resistance factors for design, for piles in axial compression. Right? We do have a table for if you want to investigate the tensile capacity of the pile. We do have a set of resistance factors as well. Basically, it's about 75% of the numbers given in this table for axial compression and converted to the resistance factors for axial tension, a reduction of 25% from the previous table. And this is the third table of resistance factors for construction control. Right? So in AASHTO specification, even in AASHTO specification, you have two tables, one for design using alpha, beta, or other methods, and you have another table for construction control too. Same thing here, you have a set of resistance factors that for construction control. Right? If you use the Iowa DOT ENR as your construction control methods, that capacity or resistance determined by the ENR formula will multiply to this resistance factors and give you the factor resistance if it's in a cohesive materials or in a mixed materials or in a non-cohesive materials. All right? If you were to use WIP and no restrike, there will be two numbers used because of two components, that the anode driving component and the setup component in a clay soil. Right? We'll talk more about this, but I'll give you a brief introduction that what you're going to see in the rest of the presentation, that how we could utilize these tables in the design. So the result of the LRFD calibrations was summarized and reported in the volume 3. It's about 300-400 pages of this report. So in terms of analysis and in terms of the reporting the outcomes of the analysis.